Hey everyone, Hugh here from LeetCode. Today we're solving LeetCode 443, string compression in Java. This is a medium difficulty problem. It comes under the string category in the LeetCode 75 study plan. At first, this problem looks like simple string manipulation. But there's an important interview concept hiding underneath. Instead of creating another array, we have to modify the existing one. That small requirement changes the entire solution. Let's understand exactly what the interviewer is asking. The problem statement says, we're given an array of characters. Our goal is to compress that array. Whenever the same character appears consecutively, we replace that group. We replace it with the character, followed by its frequency. If a character appears only once, we simply keep it. Nothing extra is written. Now here's the important part. We're not allowed to create another character array. Everything has to be written back into the same array. Finally, we don't return the compressed array itself. We only return the length of the compressed portion. So this problem isn't only about compression. It's also testing whether we can modify data efficiently. Specifically, inside the original array, let's start with the first example. The array contains A, B, B, C, C, C. Notice something. The characters are already grouped together. We have two A's, followed by two B's, then three C's. Instead of storing every character, we keep one copy of each group. Then we write how many times it appeared. So, the two A's become A, followed by 2. The two B's become B, followed by 2. And the three C's become C, followed by 3. The compressed array becomes A, 2B, 2C, 3. And the returned length is 6. Now let's look at another example. This time, the array contains only one character, just A. Since it appears only once, there's nothing to compress. The array stays exactly the same, and the returned length is 1. Now let's look at one more example. The array contains A, followed by 12 consecutive B's. This example teaches us something important. The count isn't stored as a single number. Instead, every digit is written separately. So, 12 becomes 1, followed by 2. The compressed result becomes a B12, not a B12. This is an important detail, because we're working with characters, not integers. Now we've understood what compression means. The next question is, how would we actually solve it? Let's start with the most straightforward approach. Suppose we ignore the in-place requirement for a moment. What's the easiest solution that comes to mind? We could simply create a new result. Then scan the original array from left to right. When we find a group of identical characters, we count them. We count how many times that character appears. Then we write the character into our new result. If the count is greater than 1, we also write the digits. Then, we move to the next group and repeat the process. Once we've processed every group, we have the compressed result. Finally, we copy everything back into the original array and return its new length. The idea is simple, and it's easy to understand. We'll create a temporary StringBuilder. This will store the compressed result. Next, we start scanning the array. For every new character, we count how many times it appears consecutively. Once the group ends, we append the character. If its count is greater than 1, we append the count as well. Then we continue scanning the remaining characters. After every group has been processed, we have the compressed string. Finally, we copy every character back into the original array and return the new length. The solution works. But before looking for something better, let's see it in action. Let's trace the brute force solution using the first example. The array contains A, B, B, C, C, C. We start from the beginning. The first character is A. Now we keep moving forward. As long as the character remains the same, we find another A, so the count becomes 2. The next character is B. Our group has ended. We write a then. Because the count is greater than 1, we also write 2. Our compressed result now contains a 2. Next, we begin counting the B group. Again, we find 2 consecutive Bs, so we write B, followed by 2. Our compressed result now becomes a 2B, 2. Finally, we process the C group. This time, there are 3 consecutive Cs, so we write C, followed by 3. The compressed result becomes a 2B2C3. We've reached the end of the array. Now we copy this compressed result back into the original array and return the new length, which is 6. The approach is easy to understand, but it uses extra memory. Can we avoid creating another string completely? Let's analyze the complexity. We scan the array once. That takes O of n time. Building the compressed result also takes O of n. Copying everything back takes another O of n. Overall, the time complexity is still O of n. Now let's talk about space. We're storing the compressed result separately, so the extra space required is O of n. The algorithm is efficient, but it doesn't satisfy the spirit of the problem. We're still relying on another data structure. Can we compress everything inside the same array? Let's think about why we needed another array. Whenever we finish processing a group, those characters are never used again. For example, after we've counted all the A's, do we ever need to read them again? No. We've already extracted all the information we need. That means those positions are now free. Instead of writing into another array, why don't we overwrite those positions? Interesting. Now another question appears. If we're writing into the same array, won't we destroy data that we haven't processed yet? Actually, no. And that's the key observation. Our reading position is always ahead. Our writing position always stays behind. So writing never overwrites unread characters. This gives us a very useful interview pattern. The read pointer and write pointer technique. Think of it like reading a book while taking notes. Your eyes keep moving forward, but your hand writes somewhere behind. Reading and writing are completely independent. That's exactly what's happening here. One pointer discovers each group. The other pointer writes the compressed result. Once you recognize this pattern, you'll start seeing it in many in-place array and string problems. Now let's build the optimal solution using this idea. Instead of creating another string, we'll use 2 pointers. The first pointer is called read. Its only job is to discover groups of identical characters. The second pointer is called write. Its job is to write the compressed result back into the same array. Here's how the process works. The read pointer finds an entire group, for example, 3 consecutive Cs. We count how many characters belong to that group. Once the count is known, the write pointer stores one copy of the character. If the count is greater than 1, it also writes each digit of the count. Then, the read pointer moves to the next group, and the process repeats. Notice something important. The read pointer never moves backward. The write pointer never needs to read. Each pointer has only one responsibility. That's what makes this solution both simple and efficient. Let's translate this idea into code. We'll begin by initializing 2 pointers. The first pointer is read. The second pointer is write. Initially, both start at the beginning of the array. Now we enter a loop. The read pointer will keep moving until it reaches the end of the array. For every new position, we remember the current character. Then we start counting. As long as the next character is the same, we keep increasing our count. By the time this loop ends, we know exactly how many times that character appeared consecutively. Now it's time to write. First, we always write the character itself. Then we move the write pointer forward. If the count is greater than 1, we convert the count into a string. Why? Because every digit has to be stored separately. Now we write each digit, one by one, into the array. After every digit, the write pointer moves forward. Once the entire group has been written, The read pointer continues searching for the next group. Eventually, every group is processed, and the write pointer tells us how many positions were used. So we simply return write. That's the complete solution. Now let's watch it happen. Step by step, let's use the same example. The array contains A, B, B, C, C, C. Initially, both pointers start at the first character. The read pointer begins exploring the first group. It discovers 2 consecutive As, so the count becomes 2. Now the write pointer starts writing. First, it writes A. Then, because the count is greater than 1, it writes 2. The write pointer has now moved 2 positions forward. Next, the read pointer reaches the B group. Again, it counts 2 consecutive Bs. The write pointer writes B, then 2. Now the compressed portion becomes a 2Bu. Finally, the read pointer reaches the C group. This time, it counts 3 consecutive Cs. The write pointer writes C, then 3. The compressed portion now becomes a 2B2C3. The read pointer has reached the end of the array. The write pointer has written exactly 6 characters. So we return 6. Notice something interesting. The write pointer never overwrote data. Data that the read pointer still needed. Because the read pointer was always ahead. That's exactly why this in-place technique works. Let's analyze the complexity. The read pointer scans every character exactly once. The write pointer also moves only when something is written. Together, the entire array is processed in a single pass. So the time complexity is O of n. Now let's talk about space. We only use 2 pointers, a counter, and a few temporary variables. No additional character array is created. So the extra space complexity is O of 1. That's exactly what the interviewer was hoping to see. Let's quickly recap the main ideas. We grouped consecutive identical characters. For every group, we wrote 1 copy of the character. If the count was greater than 1, we wrote each digit of the count separately. Instead of creating another array, we modified the original array itself. We achieved that using 2 independent pointers. A read pointer to discover groups, and a write pointer to build the compressed result. Whenever you need to read data, while simultaneously writing the transformed result back into the same array. Remember this pattern. The read pointer and write pointer technique. You'll see it again in many in-place array and string problems. And that's how we solve LeetCode 443. String compression. If you found this explanation helpful, make sure to like the video and subscribe to LeetCode for more coding tutorials. Thanks for watching. This is Hugh, signing off. Keep practicing, and I'll see you in the next one.